Okay, we'll go ahead and get started. Welcome to the Astrobiology seminar. I'm going to introduce our speaker today. Carol Paty comes to us from the University of Oregon, where she studies planetary science. She's also part of the Honors College there. She recently moved there. Previously, she had been at Georgia Tech in Atlanta for several years. Did some very sort of notable research involving magnetospheres. Got a lot of press about some regarding about the magnetospheres around Neptune and Uranus. Also was part of the Cassini team as a scientist, participating scientist. Is now a participating scientist as part of the Europa Clipper mission. And so she did her PhD here in the geophysics program. So I'll let Carol take over.
Thanks, Erica, so much, and thanks for having me out. I've had a really terrific day getting to meet with some familiar faces and some new faces, and just all overall, much like the last few months have felt in terms of a cross-country move from Atlanta to the West Coast, a little bit of feeling like coming back home. So thanks for having me out, even if it is the second week of class and a new job. So that's been fun. So today I thought I would talk to you. I know that the Astrobiology seminar is meant to be a seminar that brings in folks from across campus from a bunch of different disciplines. And so I tried to keep this talk at a level that I think will be accessible to all. It might not dive as deep as you might like me to into the nitty-gritty details of my own particular research, but I'm happy to talk about those. But I thought for this, I wanted to be as encompassing and inviting and welcoming as possible and get the most people on board and interested. So if you have any questions as I talk through this, please don't hesitate to stop me, and I'll try to keep things relatively on time since it's the end of the day. So the title was a little bit tongue-in-cheek. Daniel caught me at a bad moment when he asked me to give him a title in short order. So probing the interior of Europa, magnetic fields, plasma, radio waves, oh my. How do you probe the inside of a planet? But before we can get there, I think we have to really think about Europa as an icy moon, as an orbiting satellite of Jupiter, within the context of discovery and how we got to our current state of knowledge with Europa and the Jovian system. So of course we have here, and had on the first slide, some of the original kind of fun and earth-shattering paradigm-changing observations of Jupiter and its moons, where you see Galileo, having tracked the positions of these points of light in the night sky for quite some time, really was able to hone down this notion that these bright points of light were in fact orbiting around Jupiter, right? And I could go into a whole lot of detail on that, and that's why I'm sounding a little bit broken up now, because I don't want to spend too much time on this, other than to say that since its discovery, the Jovian system has been kind of a paradigm breaker in terms of changing how we think about not just Europa and Jupiter, but how we think about planetary systems in general. And I think that it continues in this path today, and I hope to show you a couple of examples why. So the Galilean moons today, a bit better than just points of light orbiting around a brighter point of light. We have many, many missions who have gone out to seek and explore and discover things about these moons over the last decades. The Pioneers 10 and 11, Voyagers 1 and 2, Galileo, Cassini as it flew by the Jovian system en route to Saturn, took some incredible images of Io's volcanism and the neutral tori and plasma tori around Jupiter. The New Horizons spacecraft, even as it flew by Jupiter, slingshotting its way toward Pluto, made incredible measurements of the Jovian system and the Jovian moons. And now we have Juno there as well, of course, not necessarily focused on the moons, but on the Jovian system as a whole. So again, we've been studying this system and trying to understand not just the state of these moons, these diverse moons, Io being much different than Europa, Europa being significantly different than Ganymede, and Callisto, by virtue of being the least studied, possibly being the most intriguing in terms of the fact that we know so little about it. But we still, while we have a better picture from all these missions of what these moons currently hold in store, what their current state is, understanding their evolution and their inner workings, how these moons are expressing themselves at the surface, be it through cracks, through volcanoes, through plumes or geyser activity, is really just tantalizing pieces of evidence in terms of understanding the interiors of these moons. And of course, since this is an astrobiology seminar, goes without saying that we have to talk a little bit about the planetary ingredients for life, right? You guys all could probably talk to me about this more than I would talk to you about it in detail. But what makes Europa so intriguing among these moons is the fact that it might be a place where we have all these ingredients together. Are they definitively there, working together in such a way as to create a habitable environment? I think that the jury is still out on that, and that's part of the motivation and the excitement behind the Europa Clipper mission, is to really suss out the details. Not just, is it possible, is it in the potential space of realities, but can we actually hone down on these various characteristics and say for certain whether, I mean, I think water, we have a pretty good ideas there. The essential elements, the chemical energy, and the stability over time, these are the questions that are more challenging to suss out and require a bit more thought. But like I said, obviously, the water, I think we have a pretty good sense is there, right? It's an icy world, and as I'll get to in a few slides from here, it's also a world that we're quite confident has a subsurface ocean, and it has more water than the Earth. And this is a nice graphic that has been used time and time again. Some of the other things that are expressions on the surface of what kind of exciting things might be going on in terms of the interior have to do with the cracks and the actual expressions of activity at the surface. Again, you have ridges, fractures, faults upon faults upon cracks. The highest resolution we've been able to zoom in and explore the surface at with Europa, you keep seeing higher and higher order levels of these fractures at the surface, indicating that it's a very dynamic moon in terms of geophysics, but also really lacking much in the way of craters, which tells you it's been evolved as a surface. There's very few craters at the surface. We also see areas of chaos, like this one here, where, again, you see evidence of something strange happening. Now, this is not just something strange. This is likely due to thermal upwelling, melting near the subsurface, and then refreezing of that matrix after some rearrangement or reconfiguration of blocks of ice near the surface. And I'll show another figure of that in a few minutes. But again, it seems like everywhere you look on the surface, with the exception of maybe that one really large impact crater there, as I tell you, there's no craters. There's like one glaring, obvious one that's staring right at you. I'm sorry, I don't have a pointer, but you can see it. But we see all these various pieces of the puzzle at the surface. One of the interesting things that I thought I would share is related to these bands, and actually what recently geophysicists and geologists have been doing to reconstruct maybe the evolution of the surface at Europa. So if we take a look at some of these bands, not only do they have differential color, which tells us something about unique composition local to these bands of material, but if you reconstruct the area around those bands, so forgetting just the color for a moment and trying to reconnect the lines, as it were, like a child doing a connect the dots, but here trying to reconnect the faults and reconstruct the patterns at the surface before this spreading may have occurred, we see, sorry, we'll try and make this work. You can actually go backwards in time, reassemble on either sides of the band all these different older fractures that had occurred before this spreading ridge or this spreading center. And you can do this at many, many locations around the surface, and this has led to a bit of a revolution in how we think about ice shell geophysics, and maybe even thinking about it more in terms of a plate tectonic setting, where you have spreading ridges, and of course, if you have spreading ridges, then you also have the counter to that, which is subduction or subsumption of surface material going, spreading, making new, subduction or subsumption, reducing surface on the ice shell. And this was brought out by Caterhorn and Proctor in 2014, and there have been several follow-on papers kind of discussing the probability, possibility, the physics behind how you would get subduction occurring in an ice shell such as Europa. But there's some other nice pieces of evidence here, not only that you have this, what seems like, and sorry, before I popped that up, this wasn't done in an animation, but you can kind of get a sense of, again, thinking about misalignment of these different fractures and bands, and then if you rotated and expanded it back out, this white area, this is missing area that might have been subducted or subsumed underneath the ice, chopped up, and then leading you to this current picture on the left-hand side. And there are other indicators that that might in fact be the case, because they have these little lenticulae, it's a little hard to see in this, but there are these little specules, little tiny spots that are also here. Since I don't have a pointer, I can do this. These guys, which look like they might be little melt pockets, little things that might be a resultant of subsumption of a plate into the interior shell and melting at the surface as a result of that. So you have this really evolving understanding of the surface dynamics, the surface geophysics of Europa. We also know, of course, that to make all of this possible, you need a form of heat, you need a source of heat. And of course, we have heat at Europa from tidal heating. And this is not only from its eccentric orbit around Jupiter, but also because it's in resonant orbits with Io and Ganymede as well, that kind of help to keep forcing Europa into this, maintaining an eccentric orbit, which allows for tidal energy to be continuously dissipated through the body. Otherwise, without those moons, it would eventually circularize the orbit and stop having all these great tidal forces on it and then freeze out, as we were discussing earlier today. But the presence of these resonant orbits with the other moons keeps kicking it out of wanting to evolve completely to a circularized orbit after dissipating that heat. So it keeps the heat pump operational over long periods of time. And what does that result in? Well, if we take a look, I'll see if this one plays. If you have thermal heating in the interior, you then have transport of that heat, much like the lava lamp scenario, or if you want to look at it from a more thermal physical model, thinking about warm flowing ice and a cold stiff ice shell, and what that means in terms of convection and moving materials up and down, allowing for differences in buoyancies from the thermal gradients, and allowing for potentially areas where you could start to trigger subsumption, as well as thermal uplift and spreading and melting near the surface. So what are the kind of the three-dimensional characteristics of the ice shell? You have different implications for habitability, and of course there was kind of the traditional older idea of having this super, super thin ice shell or a super, super thick ice shell, and I think we've kind of gotten away from those two extremes and have kind of migrated a little bit towards a more central view, but still this notion that we don't have a complete sense of how thick the ice shell is just from the Galileo observations, just from our physical interpretations of these expressions at the surface, right? And there are very different implications in terms of habitability and how material is exchanged between the surface to the ocean and the subsurface. So it's important, definitively important, if we're starting to think about this ocean as a possible habitable environment, that we understand what the exchange processes are from the silicate mantle to the ocean to the surface and back again. And I mentioned that there would be a nicer image, I probably should have put this a little earlier on, of the chaos terrain, but this notion that if you had a thermal upwelling, it might not just be that you have hot water shooting through the surface and melting it, but rather that you have a thermal upwelling that causes a melt in the ice that's focused into a very shallow melt pocket of water near the surface, and that shallow melt pocket allows for the breakup and reconfiguration of ice blocks near the surface, and then a refreezing of material. And actually over time, because of differences in volume of liquid versus frozen water, you could imagine that if you melt the ice, you would end up with a depression, right? Because liquid water takes up less volume, right? Sounds good? Sorry, just making sure everyone's still listening as I ramble on up here. Takes up less volume, so you'd end up with a depression. As it refroze, it would expand back, and you'd end up more level or even above the surface, depending on how those ice blocks reconfigured and were floating in a saline mixture. So we have some lines of evidence, and that's what we as planetary scientists love, right? Well, if we go there with a laser altimeter, or we go there with some way of mapping out the surface and figuring out, is it a depression? Is it level with the surrounding area? Is it above that? That tells you, is there still a melt pocket there? Or is it refrozen? Has it refrozen recently? Has it come back into equilibrium? So it gives you a little bit of a testable hypothesis in terms of, are these things happening now, recently? What are the time scales for these physical expressions of these types of melt processes at the surface? Of course, what I'm most excited about is Europa's magnetic personality, or the magnetic environment around Europa. Europa, of course, is orbiting Jupiter, which is a very large magnetic field, and Jupiter's rotating very rapidly. That magnetic field is tilted at 10 degrees from Jupiter's rotation axis, and therefore you have the magnetic axis kind of precessing around Jupiter. Europa, orbiting in the ecliptic, the equatorial ecliptic, is therefore seeing the magnetic field kind of oscillate back and forth over it as it's chugging along in its Keplerian orbit around Jupiter. That's a hard thing to visualize completely unless you have a nice video or me doing interpretive dance. And I'll save you the interpretive dance and go instead to the video. The blue is Jupiter's magnetic equator. The red is the satellite orbital plane, or the Keplerian orbit of Europa. And the yellow is the field line that's threaded through Europa to Jupiter. So what you see, if you just focus on Europa, is that as it goes around, it's oscillating between being at the equator above or below the magnetic equator of Jupiter. And this is happening on a very predictable periodic time scale of Jupiter's orbit, Jupiter's rotation plus the orbital Keplerian speed of Europa, right? So that's great. As a particles and fields person, what I see here is I see a dB/dt that's a nice sine wave, right? Changing magnetic field is a nice sine wave. And that turned out to work in our favor. Jupiter has provided us a perfect way to magnetically sound the interior of Europa if, in fact, there's something conductive beneath the surface. So what are we looking at here? What we are looking at here, I would argue again, is one of these paradigm-changing moments in planetary science. So you're probing Europa's interior with Jupiter's magnetic field. Here you have, essentially, the discovery of an ocean at Europa. Not only an ocean, a global subsurface ocean at Europa that is active today. So not looking at Europa's surface and saying, it looks like there's lots of cracks and fractures. It looks like a relatively young surface. It looks like that crater, impact crater, looks like it might have punched through an ice layer instead of just causing a nice impact rim and a basin. That's all lovely evidence that there might have been a subsurface ocean in the past. But this observation by the Galileo spacecraft told us that there's a subsurface ocean there now, and a global one, because, I guess so, wow. Global one. So what you see here are 3 different flybys of the Galileo spacecraft. Don't worry about the numbers, but they were in order from left to right. Over the course of a couple of years. So unfortunately with Galileo, we didn't just get to fly by Europa, fly by Europa, fly by Europa. We were touring the Jovian system, flying by all sorts of things. So we had to wait and wait and wait to get back to Europa to look at what Europa was telling us. So the E4 flyby, it was determined that there was a nice magnetic perturbation. This is Bx, By, Bz, B total. Don't worry about the real scale of it. It's the 3-component magnetic field. And what you see when you get closer to Europa, so here's where you're at the closest, is you see a nice bump and wiggle in each of these 3 components close to Europa. What does that mean? If you see a magnetic enhancement near Europa, it might mean that Europa has its own magnetic field. Well, that in and of itself would be lovely. Ganymede has its own magnetic field. We saw it, took note of it, we thought that was pretty sweet. But we went by at E14, and we saw it again, and it wasn't quite what we thought it would be. We kind of fit. And I'm using we in the royal sense here, and I apologize for that, because I'll get to we where I'm talking about me soon. In the royal sense, the planetary community looked at this and said, okay, we had the first flyby, we can fit a dipole to that. If it's an intrinsic dipole, we know what it should look like when we fly by again. It should look like a dipole. When we flew by with E14, and this is when I was in graduate school, saw that it was in fact a little bit different than expected. And you say, okay, well, with one flyby, maybe it wasn't just a dipole. Maybe it was a higher order magnetic field, had a component that we couldn't see on the place where we flew by. So it was more complex, and that's why it doesn't match perfectly. But there were musings and thoughts that, hey, maybe this could be an induction field. Maybe this is a varying field due to the fact that we had this nice periodic oscillating magnetic field upstream of it, changing every 11.2 hours. Just that we didn't fly through at the right phase between these 2 different encounters to know it. So we get to E26, I think about a year and a half later, and what you see is there's a prediction, the dotted line here. If it was a dipole or even a slightly wonky looking dipole, you might have expected it to trace this line here, or this line here, or this line here. And when you look at the actual data, which is the messy, spiky junk stuff, you see that it's completely out of phase. Well, that tells you something exciting, because it turns out when we flew by during the E26 encounter, the upstream magnetic field was out of phase compared to E4 and E14. It was on the opposite side of the oscillation. So what you're seeing is that if it was just a dipole field, or a slightly mucked up dipole field. What we saw was completely out of phase with that prediction. So this was an induction field. This is changing as you fly by, depending on what the upstream magnetic conditions are, where it is in that oscillating sine wave. And so this is a game changer, because what this did is it changed the way we think about not just icy worlds as possibly having subsurface oceans, but objects well outside of the Goldilocks zone, kind of the thermal zone for the possibility of liquid water at the surface, and shifted the idea of habitability to beyond that thermal place where water can be at the surface. It moved habitability to the class of ocean worlds where the habitable region might be beneath the surface, as long as we have those other ingredients lined up as I had on the earlier slide. To me, this is a paradigm change, and this is, again, where Europa has proven that we can think about things quite differently if we just look closer and in more detail. So what's going on? How do we do this? I've said this already with hand-wavy gestures, but now you can have the words. Periodic varying fields can generate an induction field at Europa, provided that there's a global subsurface conductor. If you just had a little melt pocket somewhere, you would not get this global dipole field. It doesn't work that way. You need a global ocean to get this nice symmetric and nicely oscillating dipole reflecting that upstream oscillation. There's actually two periodicities that exist. We could only resolve one of these with Galileo because there were only about 6 or 8 viable flybys to make this measurement. The 11.2-hour one, which is just effectively the Jovian rotation, or the Jovian rotation. No, rotation was the right word. Oh, I got stuck on that. Plus the orbital motion of Europa, right? So effectively an 11.2-hour period. There's a longer period, and that has to do with the eccentricity, that eccentricity of the orbit, the fact that on one side of its orbit, it's a little bit further away from Jupiter than it is on the other, and therefore the BZ component, the actual overall magnetic field strength, is changing as well, depending on where you are in that eccentricity. That periodicity is 85.2 hours, and conveniently, it's essentially perpendicular to the sine wave oscillation from that wobbling magnetic field. That's in the XY component, the eccentricity differences in the Z components. You have orthogonal magnetic components at different periodicities that enable you to probe different parts of the surface. The first one allows you to help constrain the ice shell thickness. The second, longer period wavelength, allows you to probe deeper into the ocean and figure out the actual ocean thickness. And when you can pull those two pieces of a convolved set apart, it allows you to solve for and constrain the salinity of that subsurface conductor as well. So it's a 3-space. You have a few periodicities. You can pull apart 2 of those 3-space and help resolve the salinity, even without drilling down into it and measuring it directly, because you can get out the conductivity. So how active is Europa today? If we just did a very simple side-by-side comparison from Voyager 2 to Galileo, you'd see that there's really no changes observed. And this is broadly, right? You're talking about a 2 kilometer per pixel resolution if you're trying to compare them fairly. 20-year period, you didn't see any differences on the surface. And that tells you that there's really not much change going on the surface over that 20-year period. However, recent observations post-Galileo, and I've only thrown one of them up here, the Roth 2014 paper, but there have been subsequent Sparks, and I'm forgetting the second paper. There have been a few subsequent papers using different observation techniques to try and figure out if there are, in fact, active plumes on Europa, because this first Roth paper was a bit at the detection limit, right? So it was really hard to feel super confident. We used it as justification up like crazy for the Clipper mission, because we said plumes, activity, got to go there now. But it took actually a few more years and a few different observation techniques, I believe, to really hone down and say, yes, this wasn't just a hot pixel or a bright sort of occurrence that wasn't reproducible by this observation technique again, because it hasn't been. But in fact, there are other mechanisms, other means of using Hubble and different wavelengths, using different parts of the telescope to look for plumes, using basically Jovian occultations and different emissions. And I think comprehensively, now that you have 3 different independent lines of evidence, you can say more confidently that they are in fact active. But in truth, we had hints of this activity before, we just didn't know how to look for it. Back during the Galileo time, we were doing stellar occultations of Europa's ionosphere, and what we found, without getting into too much detail on these, we're used to pretty pictures in planetary science. These are like line plots, really, not as exciting, right? Not a cartoon, not a pretty magnetic field picture, but very useful in that from egress to ingress, you see a large difference in the ionosphere. You're talking electron densities down here at almost non-existent, all the way up to 5,000 particles per cubic centimeter at the surface. So we knew that the ionosphere was highly variable and highly asymmetric. Ingress to egress would have been not very much time in radio occultation land, because that's during one flyby. You look across one limb, the Earth goes behind Europa, you look across the other limb, right? Every time we saw ingress and egress, with the exception of maybe this one, we saw significant differences in the peak ionospheric density. And we didn't really know how to explain it other than, well, it's got a really variable ionosphere. But it turns out one of these observations was over a thermally active spot, and we could have maybe, had we known to put all the pieces together, said perhaps that enhancement in the ionosphere was due to plume activity. Recently, just in the last year, there was a paper by Jai et al. That actually reanalyzed the magnetometer data and brought in some folks at University of Iowa to reanalyze the plasma wave data for the E12 flyby, which many had written off as just a disaster of a flyby. We couldn't make heads or tails of the oscillations and the waves in the magnetometer data. The plasma densities looked to be all over the map. And what it turns out is that, not that it's definitive, but that it can, all those odd observations can be explained by plume activity near the region where the spacecraft flew by during that particular flyby. It explains the magnetic field enhancement. It explains the enhancement in the plasma density beyond the background Jovian magnetospheric density. And so this paper also suggested that perhaps there were plumes there during Galileo. We just didn't know how to look for them, which is also interesting. So a roundabout way of getting to the fact that we have the Europa Clipper mission coming. It's a complex system, and it requires diverse observation strategies. Right? We no longer are in the age of pure, let's go there and see what we see. We are in the age of, let's go there with a set of questions that we want to answer, and what are the best observations, what's the sensitivity of those observations, and how do we use various lines of observations collaboratively and together to get at these complex scientific questions, right? These instruments have to work cooperatively, and they have to work collaboratively, because individually they're not as strong as the sum of all the observations together. And we're learning that by working in detail with the various instruments PI, and this is where the we starts to be the we me as opposed to the royal we, by working across the instrument teams and understanding just how much of the information at the surface from the camera can be used by the radar to help declutter the radar signal to really get at the surface roughness. To look at the PIMS instrument, which is measuring the plasma environment, and use that as a mechanism for subtracting out or quantifying the plasma dynamic interaction, really isolating just the induction component of the magnetic signature, so that if you're going to try and figure out characteristics of the subsurface ocean, you're not accidentally factoring in some ionospheric signal as well. And really, it's across the board. Almost all the instruments have interdependencies where they can leverage another instrument's observations to enhance their own science and vice versa. Maybe not with the same instruments. It's not always a good handshake that goes both ways, but one instrument helping another, one instrument helping another to achieve much higher order science goals. So I thought today, since this was the topic of the talk, I would look at 3 of these instruments that I've been working with significantly. I'm actually a co-I on the PIMS instrument, which are the Faraday cups that are characterizing the plasma environment, and the Reassemble, the ice-penetrating radar, which is going to be looking at the ice shell geophysics, as well as trying to remote sense the ice-water interface at the bottom of the ice shell. And the IceMag, which I'm not on directly, but again, there's this very directed handshake between PIMS and IceMag that's brought together via modeling, and that's where my little lights go off, in order to help us subtract out the plasma dynamic interaction and more completely and accurately resolve the induction signature for each flyby, and then be able to invert that over the entire mission to get at these characteristics. So I thought I would just spend a few minutes walking through each of these instruments and kind of what their overall science goals are and what techniques they're using. So this is a nice image of the Reason, the radar for Europa Assessment and Sounding, Ocean to Near Surface. It was maybe one of the more forced acronyms. as you can see up there. But you know, it has a complementary instrument on the JUICE mission called RHYME, so you have rhyme and reason, and that was worth forcing the acronym, definitively worth forcing the acronym to do that. I'm not a fan of that in general, but I think there it was rationalized well. The radar has two different antennae. It has a high-frequency 9 megahertz wave and a very high-frequency 60 megahertz wave antenna, and those are going to be able to allow us to do the sounding, the shallow, deep ice ocean interaction. So basically probing the ice shell, and I'll get into a few examples of what that means in a moment. It allows us to get a basis for altimetry. I mentioned laser altimeter earlier, but there is in fact, in the previous slide, you'll not see a laser altimeter in the instrument suite package for this mission. And it was rationalized that you didn't need a laser altimeter and a radar, because you could use the radar to figure out the altimetry and get back surface elevations, especially if you combined it with the near angle camera and were able to really resolve out all the surface structure versus the noise clutter from those observations. So again, two instruments working together at resolving a data product that's higher order than they would have been able to obtain themselves. There's reflectometry to study the surface roughness and permittivity, which gets at composition and what type of ice, what the status of the ice is. And then, of course, because the reason I'm involved on it is because it gives us the plasma as well, the plasma in between the spacecraft and the surface. It gets you a total electron content between the spacecraft and the surface, which is quite complementary to the PIMS instrument, which I'll talk about in a few minutes, which tells you the plasma density at the spacecraft. So now you have an in situ measurement as well as a line of sight measurement to the surface to combine to actually understand what the ionospheric profile is and what the ionospheric variability is, and maybe even allow you to determine if you're flying near an active region where a plume could have been. In terms of the implementation, we have some examples, or I've put some examples up here from Earth and from Mars. It says not the first rodeo for an ice-penetrating radar. That's actually really hard to say. Sounding and altimetry, we use ice-penetrating radars at the Earth. You can figure out the the surface and ice-ocean interface. You have floating icebergs, you have ice-ocean interface. These are very clean reflections in the data. And I can send you a bunch of references on this because we definitely wouldn't have time to go into all the details of the ice-penetrating radar here. For reflectometry, it gives you near surface roughness, porosity, and some indicators of composition. And we see that on Earth, these instruments are flown on small aircraft over Antarctica, which enables us to ground truth these observations as well, which we won't have that capability on Europa for some time. But it's actually demonstrated to be quite useful in terms of identifying snow versus shallow brine versus dirty ice versus light sow and fern, different categories of icy reflective materials at the surface and near surface in Antarctica. And then lastly, again, to identify active plumes, or basically look at the total electron content between the spacecraft and the surface. And here you have an example from Mars, because we flew this, the MARSIS instrument, over the polar caps of Mars. And you can see here the blue line is the actual estimated TEC, or total electron content, from the spacecraft. The green is just a Chapman fit for a given scale height and surface density, and the residuals on that give you some of the structure, and the ionosphere is dependent on latitude. So it's kind of a nice way of getting away from just a simple Chapman fit and pulling out more details of variability in the ionosphere, which in the case of Europa could be variability to a plume. So this is a slide with a lot of words, and I apologize for that, but it's just all the words I've just been saying as related to those Earth and Mars observations, which again allow us to characterize the distribution of any shallow subsurface water. So whether or not we can remote sense all the way down to the ice-ocean interface is a discussion over coffee or a beer, because the ice-penetrating radar is limited by power, right? So it only will get about 30 kilometers through the ice in ideal ice, i.e. not warm, messy ice where you're going to be losing parts of the signal. So if the ice-ocean interface is deeper than 30 kilometers, we will not sense that with the radar. And I think that's actually quite acknowledged. So I don't feel like I'm letting you in on a dirty secret of the ice-penetrating radar here. But if it is to be able, if it does in fact detect that ice-ocean interface, it'll be a very nice and complementary measurement to the induction inversion, which gets us an ice shell thickness as well, because they have those instruments and those observation lines have very different sensitivities regarding the ice sheet characteristics. So having two different lines getting you to an answer tells you something actually about the ice sheet that just having one of them you wouldn't be able to infer. But it will definitely be able to detect if there's any pockets of ice, water within the ice shell, like those near surface melt pockets and things of that nature, because you'll see them as very clear reflections in the observations. So I said search for the ice-ocean interface, investigate processes governing material exchange, and this gets at this, again, back to astrobiology, back to thinking about the communication between the surface and the subsurface. You want to understand material exchange between the ocean, the ice shell, and the surface. It's not just plumes, but I put in parentheses including plumes, but it can be even just looking at thermal profiles and looking at structures on the subsurface related to the ice sheet geophysics. You can constrain the amplitude and phase of gravitational tides, which you can also backward extract to tell you something about the Love numbers of the moon. And you can characterize compelling sites for potential future landers. That's in the recognizance fraction of that first multi-bubble chart with all the instruments labeled for the Clipper mission. So the ICE-MAG, this one may be a more straightforward acronym, not perfect, but still straightforward. Interior characterization of Europa using magnetometry, ICE-MAG, sounds quite reasonable. Again, this is what I've been talking to you about. This is to determine the European ocean's location, meaning the ice shell thickness, the ocean thickness, and the salinity. Now, these three things all factor into the induction response, but as I said, there are ways of teasing that out between the short period and long period waves, the fact that those are orthogonal signatures, and also, again, using other lines of evidence to help you constrain these things as well. In order to be able to do this, you have to actually look at the mission as a whole. You don't fly by Europa once and suddenly constrain the ocean thickness and the depth and the salinity. We don't have an orbiter, and I'll get to that slide in just a moment. What we have is a many, many, many flybyer, right? It's orbiting Jupiter, and we're going to fly by Europa like hopefully almost 60 times, but probably on the order of 50-something times, covering a large amount of latitude and longitude space and magnetic latitude and longitude space and anomaly space, trying to put together all those pieces of the puzzle that drive those periodicities and coverage and take all those data and invert it back to get out these ocean properties. What does that inversion look like? I'll show you in just a second. The other things that the magnetometer is trying to do is, of course, if there's any active plumes, those end up creating neutrals and ions that are picked up. Those pickup ions have a magnetic signature, and so we can actually see plumes with magnetometers. And we can determine the strength of the electric coupling between Jupiter's plasma and Europa's atmosphere, and basically kind of quantify the coupling of Europa and Jupiter via particles and fields. So I said, we want to look at the characteristics of the ocean. This is what we call the ICE-MAG confusogram. It is lovely and beautiful in all its glory, but it has such a wealth of information in it that it's hard to deconvolve it beyond this. What you're looking at is essentially, oh, my notes itself just say confusogram. That's great. And what you're looking at is contours of the strength of the induction fields for the short 11.2-hour periodicity in blue, or for the long period 85-hour periodicity in red. Now the contours, again, this is the strength or the amplitude of that induction signature, give you a sense as to how thick the ice shell is, because the induction is going to be determined by one, how much of an insulator is around it, as well as the conductivity and the thickness of the ocean, right? But how do you pull those three aspects apart? Well, gratefully, we have two different induction signatures, and you can see here, again, sorry, without a laser pointer, I'm looking at here instead of up there, but you can see here where there's crossovers in these two signals, where you can say, okay, if we see a 228 nanotesla short period induction signal, but we also see an 11 nanotesla strong long period signal, where these intersect start to give you a lot of information that helps you pull apart the ocean thickness and the ocean salinity. So yeah, there are some bad spaces. This space down here doesn't really have any of those lines crossing, so it's not really resolved. But everything that we've learned from the Galileo mission and the subsequent chemistry modeling, induction response modeling, we've had nothing there since Galileo, so we've had a lot of time to just do modeling, right? That's what modelers do. We actually have a pretty decent idea that the space that we're really looking at is in here, and that isn't an ultimately resolvable area if we have a reasonable conductivity, which we think we do, otherwise we wouldn't have seen the induction signal in the first place. So Galileo kind of got us to in here-ish. But as you can see, in terms of ocean thickness and conductivity, meaning salinity, that's a pretty wide range of space. But as long as we're in that range of space, we should be able to resolve it if we have precise enough measurements of these two very different periodicities. I know it's a confusing figure, so I apologize to explain it quickly. It's in the Europa book chapter, and I believe it's also in the SDT study for the lander as well, so there's longer passages on that figure in those documents. Global Web of Flybys, this is what I was saying. It's not an orbiter, but we are flying by every location we possibly can think of on this moon to resolve these things and get the best sampling of the various signals, not just local to Europa, but again, in terms of where Europa is around Jupiter and Jupiter's magnetic configuration. It also is helpful because it helps minimize the amount of time that the spacecraft spends in the high radiation environment, right? Europa's in a high radiation environment. If you were just sending an orbiter, you would have a more limited lifespan in general than if you just dive in, fly by Europa, go back out for 2 weeks, hang out in the nicer environment of Jupiter's magnetic field where you can send back all your data, then dive back in, fly by Europa, have 2 weeks to chill out, send back your data. So it's quite nice, and selfishly for me, it means that we get a chance to do Jupiter science, although we're not allowed to talk about Jovian system science until after we are much further along in the mission development. We're not allowed to say anything about Jupiter science, only Europa. For the one person in the room that will get this reference, I will just leave this there for you. One person, I heard more than one chuckle. So the last instrument I was going to talk to you about is the PIMS. Now this is a true acronym for acronym's sake. Plasma Instrument for Magnetic Sounding, PIMS. Also a lovely drink. So we have a lot of Brits on this team, so they were quite chuffed, as they say, that there was a PIMS instrument on the spacecraft, and we have PIMS glasses even, just for the toasting occasions. So plasma instrument for magnetic sounding, the science investigations. One is to determine Europa's magnetic induction response. Again, it is a plasma instrument. It's not measuring the magnetic induction response, but it is characterizing the plasma environment, which enables us to model out what the plasma magnetic interaction external to Europa is, subtract that out to be able to pull apart the internal induction field. Understand the mechanism responsible for weathering and releasing material from Europa's surface, i.e. generating the exosphere and atmosphere, and also separating that out from the plumes. And this is because it allows us to characterize the plasma, not just the electrons, but the ions as well in the local environment. The way PIMS is configured, there's 3 PIMS cups, so it gives us 3 different axial coverage and allows us to look at the pickup ions and their source locations relative to the magnetic field. And lastly is understand how Europa influences its local space environment and Jupiter's magnetosphere. Again, the dirty Jovian system science word, but we love it anyway. And that's because, of course, Europa, though a small icy world, is coupled dynamically over millions of kilometers all the way to Jupiter's ionosphere in the form of a Europa footprint in the aurora, which is really hard to see, but it's like right there. And we see this sort of coupling happening with Io, happening with Enceladus, happening at Europa and at Ganymede as well. But understanding, again, this complex interaction helps us to subtract out the alphane interaction from the magnetic signature and really fully resolve the induction or the internal contribution to the magnetic field measurement. Modeling is important in this endeavor. We cannot just measure the plasma, measure the magnetic field, and suddenly magically know what component of that magnetic response is from the internal versus the external environment. This map is actually one of my favorite ones from our original instrument proposal for PIMS, and it just shows in blue where, if for a given set of flybys, this was an earlier proposed suite of flybys, where your induction field would dominate your signal versus where the plasma interaction would dominate your signal. Of course, where it turns to green, there's nothing. This is a very localized interaction over an Alphane wing. So once you're out here, it doesn't matter anymore. You're really just interested in the local Alphane wing interaction at Europa. And you see a lot of this is plasma dominated on approach. And then you get closer, and there are regions, especially in the upstream as opposed to the wake, where you can see that the induction field is clearly dominant in your magnetic signature, but a lot of the space is going to be dominated by the plasma interaction. It's not just measuring the plasma density, it's then being able to take that and the local field environment, model it, and figure out how much of the magnetic field is going to be coming from the plasma dynamic interaction with the Jovian system plasma, and how much is going to be just the residual dB/dt that's creating the induction field all the way down to the ocean. You model that, then you can subtract it out. Then you can do your grand inversion over all those Tholian web flybys and back out your ocean characteristics. So characterizing the interior is a complex problem. You need to do all these things. I've said these words already at least 5 times, so I won't say them again because I want to keep things on time. You have to know the plasma environment. You have to be able to model the external response, and then you have to perform many, many flybys to cover your local variable space to back out the inversion, to get at the internal structure. I said I wouldn't talk about the modeling in detail because there are those here at UW that can teach whole classes on it, but I do love this. The sun's atmosphere is a super hot plasma governed by magnetohydrodynamic forces. Ah, yes, of course. Whenever I hear magnetohydrodynamic, my brain just replaces it with magic. So I am a magician, and that is what I do. And I have been told that there's magic in my code more than once. So I'll leave it there for naughty reviewers to assess. So concluding thoughts, Europa has provided a rich environment for discovery and paradigm change. And I say this not just tongue-in-cheek because of Galileo, but because we basically invented ourselves as astrobiologists an entire new category of habitable worlds in the ocean worlds that reside far beyond the classical Goldilocks zone. Or maybe we're just redefining the Goldilocks zone, however you like to say it. The complex science in this mission goes beyond just taking a look at something we've never seen and trying to discover something new. We're at a point in our development in terms of these missions that we have really higher order science questions we're looking to answer. And to do it, you can't just send one really good instrument. As much as the ice-penetrating radar thinks it's the most important instrument, as much as the magnetometer thinks it's the most important instrument, okay, let's be honest, the plasma, we always know that we're the most important instrument. But I think in this game, we actually know that we're more of a supporting character in terms of answering the primary goal of the mission, which is helping IceMag to be able to resolve the part of the measurement that they make in terms of the interior and not the exterior science. So it's really through a diverse instrumental approach and cooperative, and definitively the most time I spend on telecons is figuring out the cooperative data plans and how these instruments are going to communicate the information to one another in a way that is most productive for everyone involved, is how we're going to get to the answers of these questions. So I leave it with Go Clipper and open to questions. So, any quick questions? Yeah.
When is this mission set to launch?
The beginning of the launch window is 2022, so it could be any time after then. A lot of that, the mission time scale is going to determine our ride, what kind of launch vehicle we use, whether we're on a Vega trajectory, so Venus, Earth, gravity assist, or whether we can be on a heavy launch capability, direct home and transfer trajectory to get us directly there in a much more rapid frame of time. We don't know yet what our launch vehicle is. There's murmurs afoot, there have been for a year, but that will determine the timescale of the project. The launch date, like I said, it opens in spring of 2022. I'm an optimist, so I have to believe that we will launch shortly thereafter, but it is just the beginning of the launch window.
You did not give any details, obviously it hasn't been finally worked out, but you give a feeling for the resolution of the radar, how often you'll be repeating a given region to look for time variations, and also degree of completeness
Those are three very excellent questions strung together. There has been a lot of thought given in terms of coverage. Some of that coverage is limited by orbital mechanics. They're trying to tweak that to give us coverage in the most desired areas for geology, geophysics folks, and that's an ongoing debate. But some of it, there are some areas that are just very challenging to get coverage on, and so they're going to remain poorly covered. But there was a lot of attention given to that coverage, as well as given to crossover points, so times where you can go over the same space at different, or at similar-ish altitudes and get those crossover points to look at the tidal flexure and actually motions to get at the higher order gravity terms, or as high order as we can with that. So I can say that there are at least 8 pairs of crossover points. I can't remember what the final count was because the orbit tour keeps evolving. In terms of the resolution coverage, that has evolved so many times, I don't know what the current answer is, other than that between the radar and the NAC and the WAC, so the near angle camera and the wide angle camera, they are trying to get as good a coverage as possible for reconnaissance, as that's the third leg of the mission, is really figuring out a way to determine where you would put a lander down. So that's far within the realm of contemplation in terms of the orbital tour development.
And what fraction of the surface do you hope to pass at least once with the radar?
I don't want to say the wrong number. I have it in many, many backup slides on the radar, but I don't want to misquote it.
More than 50%?
Yes. Yeah. Dawn and then Erica.
So what's the expectation on the dissolved component of the contents of Europa Ocean compared to Earth's?
The expectation.
Yeah, because there's all kinds of interesting things that can go on. One thing is a different body,
Yeah.
and so it might to be quite different than Earth's ocean. But also, with its ice and water, you must have a large amount of fractionation. Some places that probably have very high salt contents.
These are, yeah, I mean, these are a great question. I think the first step in that is to resolve the question of what the salinity is. And I think the higher order question is salinity, thinking about it as a constant salinity over the entire ocean is probably an oversimplification. I think that's where you were going with that you likely will have a different salinity at the interface or close to the interface, or possibly at different important pressure transitions. Where you might have different phases or different stabilities of different salinities, right? Just like you can have different salinities in deep parts of our ocean where you have a bit of a boundary that traps things. And I don't think that we are at the point now. There are many people looking at things like this, like Steve Vance, another UW alum. But I don't think there's a resolution to that question because it's so unconstrained at the moment. The first step is to get a kind of height integrated overall salinity and conductivity, and from there, once you start to know the depth of the ocean, then you can further constrain the thermodynamics and the aqueous geochemistry within those pressures and depths, and try to pull out more detailed information on the gradient of the salinity, and maybe even the gradient of the composition related to that. But I just don't think we're there yet, because we have too many open parameters still. Not that people aren't thinking about it, but that we don't have a good way to constrain it beyond what we learned from Galileo.
And also, chlorine content of a body like that is a huge question.
It is a huge question mark. We don't even know what exactly the content would be that has given it the salinity that we've constrained it to be so far. Yeah. Erica, you had a next question.
When the funding for Europa Clipper was initially allocated by Congress, there was funding for a lander as well. I'm just curious, because you were mentioning that one component is for
reconnaissance.
For the lander. Yeah.
It's not for the lander. It's for reconnaissance in general.
Okay.
But
So they reworked it that there won't be a lander
oh,
component.
it's not, well, so the lander funding, this is a complex minefield at the moment. If anyone was listening into the OPAG meeting last month, which I was at and trying to moderate, and I'm still writing up the findings for. But we had a panel discussion on the lander. The lander is still very much in play, but the lander is not tethered to Clipper. Clipper and the lander are two different things. The only way in which they are tethered is that the Europa Clipper may be able to provide reconnaissance that will aid the lander depending on when the lander's launch date is. But the budgets for those two missions are kept completely separate, and the lander's budget is by no means a new start for a new flagship mission. It's still in process of getting sussed out. There was the SDT, which I saw on a few folks' desks, David, for the Europa lander, but they are still at a very much developmental phase on that, and by no means have a fresh start for a new flagship. And these will be questions that will be answered as we move on towards the next decadal. This question.
Yeah, I'm just curious. So when you get the data back from all these flybys, how are you going to do that grand inversion? Because presumably the magnetohydrodynamic code is pretty complicated. You can't just run it 10 million times to sweep out the parameter space. How do you?
You have to run it 10 million times. You only have to run it 50 some odd times.
Is there enough
Well,
constraints to just?
well, the hope is that the constraints will be there from the in situ observation. So right now what we're doing is we're running multiple groups, magnetohydrodynamic and hybrid codes. We're trying to get some hybrid modelers on board as well, to rough out the parameter space before we even launch. But you're right. How do you suss it out? The hope is that by having the plasma detector and the magnetometer together for each flyby, that upstream of the interaction zone, you know what the upstream plasma density is, you know what the local magnetic field from Jupiter is. As you get closer, you can use the radar, the reason data, and the in situ plasma measurement to constrain what the ionosphere, the local plasma near the surface is. And with those components, you can in fact model it out, and try to then figure out what component of the observed magnetic signal is from the alphane wing interaction, essentially. And you can analytically do that to a rough order as a sanity check, but to get to hone it down is a pretty critical part, and the modeling actually plays a large role. You'll see now, I think, at the complexity of the questions being asked in missions today, missions like this one, missions like MAVEN, had a very significant modeling component, because the measurement alone is not enough to answer the question. You have to be able to deconvolve it. But yeah, I think at the end of the day, even though people are resistant to it, unless they're very similar flyby conditions, I would say you just run a model for each of the flybys when you're doing it. If you can do it quick and dirty and do the inversion, but you're going to have a couple of years as you do all these flybys to build up the data set, so you might as well do the model run simultaneously and pull out the information as you go before getting to the big inversion part. The inversion itself isn't super challenging once you've done all the legwork. So.
I can ask another practical question. In these flybys, how are you able to share time with the instruments? Probably they all can't work on a given flyby, and maybe they can.
The desire and the mission architecture was to make it as not like Cassini as possible in terms of complexity and sharing data bandwidth. Having to plan every single moment of Cassini as a fist fight between instruments, or a trade swap, I shouldn't call it a fist fight, but as a bite battle between instruments. I just made that up. I'm quite proud of myself. Is not economical and is not useful, especially in something that has such a repetitive geometry. So the idea is that there were going to be as much of the mission was going to be on repetitive mode as possible, with perhaps a few of the most critical orientations, say for a surface observation, to be given to a camera, or to be, if it was a critical one for the magnetic inversion. The plasma and magnetometer instruments are not super heavy eaters of bandwidth and energy, so they mostly are on.
Well, so the bandwidth, of course, is critical, but I also think just the geometry of the spacecraft.
Yes, this is true, and that's.
Are you
We're trying
about
to.
that, please?
That is always the accommodation on the spacecraft is a continuous battle, but I think for the most part, the instruments are accommodated to be able to work pretty optimally. The trickiest part is actually for things like the radio occultations and the UV camera, because they want to be able to turn and look back at Europa after they go by, which might be challenging for that camera and radar and configuration, because it's not during the flyby, it's after the flyby. That is posing some challenges in terms of who might get priority for when, if there's a plume, how do we say, okay, the UV camera gets to turn and look at that regardless of what the antenna wants us to do. Not the data antenna, but the other antenna, right. And so I think that those trade spaces are still being detailed, but those are kind of trade spaces for the unknowns. I think for the knowns, it's pretty well mapped out, actually, who gets priority when. And it's as much of it as repetitive operation as possible, because they didn't want it to be like Cassini, where who gets to look when. We're going through the plume, this guy gets priority over this one, and things like that. If you'll allow me 2 extra seconds, I have like a few, throughout the talk, I brought up the notion of kind of a diversity of instruments working cooperatively. And one of the things I try to do at the end of each of these talks is take 1 minute to talk about diversity and cooperation on the Europa Project Science Group, as well as in NASA missions and hopefully all of our missions in general. This is a zoomed out picture of us at the first PSG meeting in August of 2015. It's hard to see when you're that zoomed out, but it's actually quite a diverse team of people that are working on the Europa Clipper, and something we're actually actively engaged in and working toward enhancing at all aspects, not just the scientist side, but the engineering side, the project side, to make a possibility. And something I'm pretty passionate about in space plasma physics, because as you can imagine, space plasma physics hasn't always been the most habitable environment for diversity. This is one of my favorite pictures. This is a workshop on the structure and dynamics of the Jovian magnetosphere, very relevant to Europa Clipper in 1977. This was leading up to Voyager's arrival at Jupiter. And you'll see here a very diverse cast of characters, a who's who of people in space physics from Ian Axford, James Van Allen, Alex Dessler, George Sisko, Don Gurnett, Carl McElwain. Phenomenal group of people. One of these is not like the other. And that would be Margaret Keevelson down there in the corner, if you couldn't tell, smiling as she always does. And what's unique about this, and I've talked with her at length, and she's given several seminars on this, is just you know, how times have changed. This is the plasma instrument team for Clipper, and it's a slightly different story, with Margaret Keevelson still front and center for scale from the previous image. She is still dynamic and active she will be turning 90 this fall. She's holding there, you can't tell because she's wearing a black shirt, but she's holding the monolith award for her fundamental work in finding the Europa subsurface ocean from the magnetometer data on Galileo, and hence that was kind of an important stepping stone to getting us to the Clipper mission today.